All right, AP, let's get started on Chapter 4, looking at the first section here, talking about water. We're going to move into aqueous solutions. Aqueous involves water, so let's start by understanding what water is. I want you to be able to draw and or interpret representations of solutions that show the interactions between the solute and solvents, a couple terms that you'll have to define. Create or interpret representations that link the concept of molarity, it's going to be a new idea in this chapter, with particle views of solution. Again, understand in the very concept of what's going on, picture the individual molecules and what's happening between them. It'll help you in the long run. Then evaluate the classification of a process as a physical change, chemical change, or ambiguous change based on both macroscopic observations of the distinction between rearrangement of covalent interactions and non-covalent interactions. So let's get going. It's going to be a longer one. So we're talking about water. Water is one of the most important substances on Earth. It can dissolve many different substances, both ionic and non-ionic. Now, obviously, it can dissolve ionic compounds because of this strong polarity that it has, but that polarity also allows it to dissolve non-ionic substances as well. For example, we have this hydrocarbon down here. This is C2H6O. If we introduce this hydrocarbon to water, and we try to dissolve it in water, there's going to be two different types of interactions. You're going to have the interaction, or should I say there's going to be one type of interaction mainly for this particular type. You're going to have the interaction between the partial positive hydrogen atom from the hydrocarbon and the partial negative charge of the oxygen in the water. Now, but you also see if there's going to be more waters here, you're also going to see some interactions between the partial positive of the hydrogen on the water and that partial negative on the oxygen on the hydrocarbon. But we're just highlighting one interaction right here. But again, it's a partial positive plus a partial negative. Again, this is why even though the polar nature of water allows it to dissolve non-ionic compounds, the interaction, this hydrogen bond, which is not actually a bond, it's just an intramolecular force, is not as strong as an ionic bond, because an ionic bond takes place between two full charges. Here, they're both partial charges, so they're less than one full charge, and so they're not going to be as strong as any ionic bond. Move on to some definitions that we need. Solution is a homogeneous mixture. Okay, it doesn't have to be aqueous. Of course, aqueous is an example of a solution, but you can mix metals together. Okay, that is a solution. Alloys like steel, they're solutions of metals. They're just homogeneously mixed together. Solute is what's getting dissolved. Okay, so if I put some, for example, salt in water, salt is the solute. Okay, it's getting dissolved, meaning there's less of that salt. Solvent is the thing that's doing the dissolving. There's more of that. If I'm going to throw a little bit of salt in some water, yeah, I'm going to have a large amount of water. Maybe it's a glass of water or a pot of water on the stove. There's going to be more of the solvent than the solute. And for the most part, we're going to be talking about water as the solvent in this chapter. Soluble means it can be dissolved. If something is said to be soluble, it means it will dissolve in water. If something is said to be insoluble, it means that it can't be dissolved. We also have the word miscible. Okay, miscible. It's liquids that dissolve in each other. Let's see here. Okay, moving on to solubility. Okay, solubility. We just talked about if something is soluble, it means it has the ability to be dissolved. So solubility refers to the extent to which it will dissolve, how much of a substance will dissolve in a given amount of water. Typically, this information is going to be communicated in grams per 100 milliliters. Now, solubility is going to vary greatly, but if that substance does dissolve, the ions are being separated, and then they can move around. Remember that water is having interactions between the partial positives and partial negatives of the water and either a full negative or positive charge or a partial negative or positive charge from that solute. Because of that, it's going to pull those things apart and allow them to move throughout the rest of the water. Water can also dissolve non-ionic compounds if they have polar bonds, or not necessarily even an ionic bond, just a polar covalent. Again, because when you have polar covalent bonds, you're going to have partial positives and partial negatives, and that is what the polar nature of water is going to be working on. So now we get to talk about aqueous solutions. It's a very fancy sounding term for something is dissolved in water. Now, water is a very good solvent because the molecules are polar, we just talked about, and we can see over here on the right. The oxygen atoms have a partial negative charge, and the hydrogen atoms have a partial positive charge, which is actually a pretty large partial charge here, because the difference, the electronegativity difference between oxygen and hydrogen is actually pretty great. So those electrons in those bonds are going to be a lot closer towards the oxygen. Water does have a bond angle of 105 degrees, not degrees Celsius. That is a typo. I do not know why that's in there. It's a bond angle of 105 degrees. Now, let's look at a representation of the process of hydration. Okay, hydration is a specific term that describes the dissolving of something in water specifically. The hyd beginning of this term refers to water specifically. So if I have some sort of like ionic something, some ionic salt over here, you see the alternating positives and negative charges for that lattice structure. You can see that both the positive and negative ions are going to get plucked out from that solid, and then they're going to be able to start moving around through the rest of the water. Now, the positives are going to get plucked out by the negative sides of the hydrogen, or of the oxygens that we see right here. The positives are getting plucked out. Notice that they're oriented towards the oxygens, or vice versa. You could say the oxygens are oriented towards the positives. But the negative ions are going to be oriented towards the hydrogens. And because of that polar nature of water, this water is going to be able to pull away both positive and negative ions in this salt, making this solid disappear.
An ionic solid dissolves in water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
All right, moving on to section 2, we're going to talk about the nature of aqueous solutions, specifically electrolytes. Now, I'm sure you've heard that word before. Gatorade's got them. But what exactly do electrolytes mean? What are they? We're going to talk about that a little bit more specifically. In this section, we're not going to be introducing anything that's super complex in terms of concept. The only problem is there's going to be a number of them, of the simpler things. So that's the type of challenge that we're going to be looking at in this section. All right, so the same 3 learning objectives that we've been looking at for a while now. Okay, those first 2 bullets. On a very specific level, I want you to be able to identify electrolytes and acids as strong, weak, or non. Okay, so there are 6 different ideas here. We can have non-electrolytes, we can have weak electrolytes, and strong electrolytes. We can also have something that's not an acid, a non-acid, even though that's not really a term, but something that's not an acid. You need to recognize something as an acid and a weak acid. And then lastly, something as an acid and a strong acid. Okay, again, each of these have a fairly simple definition, but again, there's a number of these new things here. So here we go. So as a quick reminder, we're talking about aqueous solutions, so we have a solute and a solvent. Solute is a substance being dissolved. The solvent here is liquid water because we're talking about aqueous solutions. The new idea here is the electrolyte. It's a substance that, when dissolved in water, produces a solution that can conduct electricity. Now, electricity is a result or kind of like a byproduct of what the electrolyte is actually doing in solution. So when you have a strong electrolyte, okay, it's going to be conducting electricity very, very brightly. And when you use electrolytes in contraption that we'll see on the next slide, you can conduct a lot of electricity, meaning that if you hook a light bulb to that bulb is going to shine very brightly. What's happening here is that electrolyte is being completely ionized in the water, resulting in almost exclusively ions in water. If we go back to that idea of hydration, if every single bit of that ionic salt is dissolved, is hydrated, we know that that's a strong electrolyte because it's completely dissociated in that water. And since you have all those individual charged ions moving around, you're going to be able to conduct electricity very well because of that. So here's an example. NaCl is a strong electrolyte because when you put NaCl in water, you'll essentially have no NaCl formula units left in the solution. They'll all break up into Na plus and Cl minus. But you can have a weak electrolyte, which is only going to conduct a small current, so the bulb will glow, but pretty dimly. It'll be very noticeable. And what this means is you're only having a small degree of ionization in the water. And so that idea of hydration, yes, it is happening, but not nearly to the extent of a strong electrolyte. So you are getting some of those ions breaking off, but you are still going to have a large amount of that original substance in the water still as well. An example would be ammonia and water. This reaction is actually is reversible. It goes back and forth. So at any given time, you are going to have in the same solution ammonia, the NH3, the H2O, as well as the NH4 plus, the ammonium ion, as well as the OH minus, that's the hydroxide anion. All of those things are going to be present in water for this particular solution. Now, yes, you do have some of these ions, the ammonium and the hydroxide, so you're going to conduct electricity, but you're also going to have plenty of that ammonia over there. That's a molecule. It's not charged. It won't conduct electricity, or won't ionize, I should say. And so that's not going to help you conduct your electricity. So that's why you're only conducting a small current. You can also have non-electrolytes. There's no current flow. The bulb will not light up at all. And so this means that, yes, this non-electrolyte is dissolving into water, meaning they're breaking apart from one another, but the unit never breaks down to produce any ions. Okay, so when you look at the solution, you have almost exclusively whole molecules in the water floating around within the water. Okay, now the molecules aren't all bunched up to make some sort of precipitate, but they're individually molecules, no ions. So table sugar, for example, very soluble. You can mix sugar into water, and you won't see the table sugar anymore, but it's not going to produce any ions in that dissolving. So here's a representation. If we actually take a light bulb and hook it up to some electrodes and run it through these different aqueous solutions, if I have a non-electrolyte, notice that the bulb is not on at all. If I have a weak electrolyte over here, C, the bulb is on, but not quite very brightly. And then for B, we have that strong electrolyte. It's going to be a very, very bright bulb. So electrolytes, they dissociate to produce ions. Okay, if when they break apart, they produce ions, that's an electrolyte. The more the electrolyte dissociates, the more ions it produces. And the more ions it produces, the more electricity is being conducted. That's the idea behind electrolytes.
Strong electrolytes dissociate completely to give ions in solution that conduct electrical current. Soluble salts, strong acids, and strong bases act as strong electrolytes in solution. Weak electrolytes dissociate to a small extent to give only a few ions in solution available to conduct electrical current. Weak acids and bases are the most common weak electrolytes.
All right, so is it a strong electrolyte, a weak electrolyte, or a non-electrolyte? Here are some examples that you're going to need to memorize. You're not going to have access to these tables on an exam. You're going to need to remember these things. So strong electrolytes include any sort of strong acid, any sort of strong base, or any water-soluble ionic compound. Okay, if it's ionic and it's soluble, that bad boy is going to dissociate quite strongly. So for the strong bases, that hydroxide is an OH base. That 1A and 2A, that just means a hydroxide that is bonded to any metal from main group 1 or main group 2. Okay, the alkali metals or the alkaline earth metals. Or is it a weak electrolyte? Any sort of weak acid or weak base. And there are actually a couple of ionic compounds that fit into this category. But what you're going to be mostly memorizing are the strong electrolytes. And then lastly, a non-electrolyte, basically anything that is molecular, right, covalently bonded, or organic, okay, because most organic compounds are molecular, covalently bonded. All right, section 3, the composition of solutions. Now we're going to get to the point where we're actually calculating some stuff. So here we go. So what I'm wanting you to do, to be able to connect the number of particles, moles, masses, and volume of substances to one another, both quantitatively and qualitatively. Again, doing stoichiometric conversions here, calculations. Draw and or interpret representations of solutions that show the interactions between the solute and solvent. Again, how many times have you seen a picture of individual molecules in water so far in this presentation? That's how I want you to think about what's happening. Create or interpret representations that link the concept of molarity, and we're going to introduce that in this section. With particle views of solution. Calculate the molar concentration of a solution, or the quantities of solutes and volumes of solution that are related through molarity. After that, perform dilution calculations and then use molarity as a conversion factor in stoichiometric calculations. All right, quick reminder. Solute, it's the substance being dissolved. Solvent is the substance doing the dissolving. Concentration is the new thing here. The concentration of a solution is the quantity of the solute, the stuff being dissolved in a given quantity of solution or solvent. So we actually have to have two pieces of information to calculate this: the amount of solute and the amount of solvent. So a concentrated solution contains a relatively large amount of solute versus solvent, meaning there's a lot of the solute per solvent. A dilute solution contains relatively small concentration of the solute versus how much of the solvent you have. But here, concentrated and dilute aren't quantitative, meaning there's no numbers here. I can't tell you exactly how concentrated or exactly how diluted they are. So we use the idea of molarity or molar concentration. I like to use the term molarity here, so you hear that from me more often, but molar concentration is another way to say the exact same thing. It's the amount of solute in moles per 1 liter of solution. You can see it's actually a pretty simple calculation here. The molarity is equal to the however many moles of the solute you have. And again, you can calculate that pretty darn easily stoichiometrically by this point. Then however many liters of the solution you have. So a solution that is 0.35 molar, that's how you read that, molar, sucrose contains 0.35 moles of sucrose in each liter of solution. For every liter of solution, you have 0.35 moles of sucrose. But keep in mind that the molarity signifies moles of solute per liter of solution, not liters of solvent. It's the total solution, So if I'm going to prepare potassium permanganate, and I wanted to have a very specific concentration, like this 0.01000 molar, okay, I'm going to go through a couple steps. Well, I'm going to weigh 0.01000 moles of that potassium permanganate. That ends up being 1.580 grams, just FYI. I'm going to place that into some water. How much? Doesn't matter right now, just get it in water. And then lastly, we're going to add water until we reach that 1.000 liter mark. Now we have 1 liter of solution, and it has 0.01000 moles of potassium permanganate. So this is a 0.01000 molar solution of potassium permanganate. So here's a concept check. I'll give you the answer for this one, but please try this on your own. What is the molarity of a solution in which 33 333 grams of potassium hydrogen carbonate. Check that on your polyatomic ion sheet if you still have that, or just Google image search that. You'll be able to find it pretty darn easily. Hydrogen carbonate is a polyatomic ion. That's why I told you that. If that's dissolved in enough water to make 10.0 liters of solution. You want to press pause? So we're using this this form of calculation here. Molarity is equal to moles of solute divided by liters of solution. And so with the information that we're given from this problem, I'm going to convert that 333 grams of potassium hydrogen carbonate into moles of potassium hydrogen carbonate. And that's why we need to know what the formula for that is, so we can know exactly what the molar mass of it is, because we're using the molar mass as a conversion factor so that we can have the moles of solute. Now we have 10.0 liters of solution, so 10.0 liters of solution goes on the denominator, and we end up with 0.333 molar potassium hydrogen carbonate. All right, here's another concept check. I'll give you the answer here because I'm a nice guy. Which of the following solution contains the greatest number of ions? Go ahead and press pause so you can calculate this on your own. All right, it's actually B. A contains 0.08 moles of ions. C contains 0.08 moles of ions. And D doesn't end up making any ions because it's sucrose. That's table sugar. No ions, 0. But B actually ends up having 0.09 moles of ions. Here's a concept check. I will not give the answer during this presentation. Check with your classmates or myself through a different avenue to check your answers on this, but please try it. Moving on to another concept check where I will give the answer. So the label of a stock bottle of aqueous ammonia indicates that the solution is 28% ammonia by mass. Okay, well, what's by mass? That's a clue right there. It has a density of 0.898 grams per milliliter. Calculate the molarity of the solution. Well, remember, in order to calculate the molarity of a solution, we need the moles of the solute first and the liters of the solution. So we're going to have to do a few preliminary calculations. So we will find it the most convenient to base the calculation on a 1.00 liter volume of the solution because it's a nice round number. When we have found the number of moles of ammonia in this 1 liter solution, we will have the molarity. So the way in which these factors enter the calculation is going to be outlined. So we're trying to find the moles of NH3, ammonia. Now we don't have a mass of ammonia. We have percent ammonia. But we can take that and over here, okay, we can take that and assume that it's a percentage of 100 grams. Because remember, that whole trick for mass percent calculations, assume a 100 gram sample. It makes everything super simple and super easy. So we have our 1 liter of solution. Okay, our 1 liter of solution is correct, but this density number right here is in milliliters, not liters. So we'll convert our liters of solution into milliliters of solution. That's going to allow us to have milliliters of solution as our unit. And so when we set up the density, okay, given to us by the problem right here, the density as a conversion factor, that allows the milliliters of solution to cancel out, leaving grams of solute. Okay, and then we take the mass of ammonia. Again, that is a mass 28.0 grams per 100 grams of the solution. Yeah, that's 28%. But what it allows us to do is go from talking about grams of solution into grams of ammonia, because that's what the question needs. We need molarity, but in order to have molarity, we need the moles of ammonia. And then using the molar mass of ammonia, we can calculate the moles of ammonia. That gives us 14.8 moles of ammonia, because 14.8 moles of ammonia are present in 1.00 liters. The solution is 14.8 molar. That is to say, boom, there's your baseline calculation. Here's a concept check for you guys to try. I'm not going to give you the answer during this presentation. Check with your classmates or myself through a different avenue so you can double check that you got the right answer. Now we're moving on to the back end of this presentation, dilution of solutions. Dilution is the process of preparing a more dilute solution, dilute, by adding solvent to a more concentrated one. Okay, so you have a certain concentration. If you add solvent without adding more solute, you dilute that solution. So addition of a solvent does not change the amount of solute in the solution, but it does change the concentration. It's very common to prepare a concentrated stock solution of a solute and then dilute it to other concentrations as you need. So here's a visual representation of diluting a solution. We start and end with the same amount of solute. Okay, in this example, we have 0.0050 moles of iodine. That's not going to change. But we add solvent that decreases the concentration because it's making the number we're putting on the denominator larger. You can see the difference between these two molar concentrations down here. So if I ask you a question or you are asked a question about ion concentration in solution, here's what we do. What is the concentration of sodium sulfate in a solution prepared by diluting 0.010 moles of sodium sulfate to 1.00 liters? Now the answer is going to be 0. Why? What's the concentration of Na2SO4? How are we communicating this? Well, it's a little bit of a trick question, okay? Because in solution, the Na and the SO4s, they're going to split up into individual ions. You're not going to have any of that formula unit Na2SO4. They're going to split up. So what I'm really going to have in 0.010 molar sodium sulfate, I'm going to have 2 moles of Na plus ions. And so I'm going to represent that as a concentration of Na plus in brackets. Okay, that denotes concentration. It's 0.020 molar. But there's only 1 mole of the sulfate ion, and so we're going to represent that as, again, in brackets, it's only 0.010 molar. So there are actually 2 different concentrations in, let's go back to this, in this solution. So you can't ask or answer what's the concentration of this formula unit in solution because it's going to break up. You're actually going to have 2 different solutions. Now an ion, just real quick, an ion is only going to have 1 concentration in a solution. Okay, even if the ions come from 2 or more different sources. Okay, like in this example, it's sodium sulfate, and I add some sodium chloride to this. There's only 1 concentration of sodium ions because all of the sodium ions are the exact same. It doesn't matter if it came from the sodium sulfate or the sodium chloride; those are all the same. So even if there's 2 or more sources of one of the ions, it's just 1 concentration. So if we're actually going to try to do some calculations here for dilutions, the moles of solute do not change on dilution. Okay, right? We're only changing the amount of solvent. Now we can easily find out the moles of solute by multiplying the molarity of the solution by the volume of the solution. That way, the volume on molarity will cancel out. You'll be left with moles. Now, we can take this calculation and we can apply it to something a little bit more useful for us in this course. I have 3 different representations of the exact same thing. You may have seen different versions of it in different places. The calculations are all the same. It's just, is it sub-concentrated or sub-diluted? Is it sub-1, or sub-2, or sub-initial, sub-final? They all mean the same thing. Okay. I, in my mind, have always been a little bit easier for me to do the M1 V1 equals M2 V2. It's always been a little bit more straightforward in my mind, but whichever one of these works for you, use it. Speaking of using it, let's use it. How many milliliters, now notice that molar there is in liters, so we're going to have to do a conversion there. How many milliliters of 3.0 molar hydrogen sulfate are required to make 450 milliliters of 0.10 molar sodium sulfate? So we are given the molarity here of a more concentrated solution, okay, 3.0 molars, and the volume molarity of a more dilute one containing the same solute. Okay, the same amount of solute. We're not changing how much hydrogen sulfate's in there. We're asked to calculate the volume of concentrated solution that needs to be prepared to dilute the solution. So we're going to use the M1V1 equals M2V2 equation, where M1 is the molarity of the more concentrated solution. Now, because of this, we can rearrange the original equation so that we're actually solving for V1. We're actually going to solve for that, which is what we need, plugging in the values that we were given from the equation, or from the problem. We generate 15 milliliters. We see that if we start with 15 milliliters of 3.0 H2SO4 and dilute it to a total volume of 450 milliliters, the desired 0.10 molar solution will be obtained. The calculated volume seems reasonable because the small volume of a concentrated solution is used to prepare a large volume of a dilute solution. All right, I want you guys to try these two on your own. I'm not going to give you the answer right now. You're going to have to check with your classmates or myself through some other avenue. We're going to finish up with, oh, not quite yet. Sorry, my bad. Molarity provides an additional tool in stoichiometric calculations based on chemical equations. We're still using chemical equations. We're still doing stoichiometric calculations. Molarity is just yet another thing, another tool we can put in that stoichiometric toolbox. So molarity provides conversion factors, right? Factors for converting between moles of solute and liters of solution. Again, the exact same things we've been doing so far. So if substance A as a solution of a known concentration, we can start with the molarity of A times the volumes of solution of A to get here, right? Because then we'll have moles of substance A. Then we can simply convert into moles of substance B, okay? Then we can go from the moles of substance B to either volume or molarity. All right, we got a concept check. I'll give you the answer here. Looks like one of my animations are a little whacked, so let's get started here. A chemical reaction familiar to many geologists is the one that is used to identify limestone. The reaction of hydrochloric acid with limestone, which is largely calcium carbonate, is seen through an effervescence, a bubbling due to the liberation of gaseous carbon dioxide, according to the following balanced chemical reaction. How many grams of calcium carbonate are consumed in a reaction of 225 milliliters of 3.25 molar HCl?